We are from Roy's Academy faculty team, and today we'll learn Course CBSE Class 10, Subject Mathematics, Chapter 6, Triangles, Topic Geometric Similarity and the Principle of Proportion. For obtaining similar video explainers, please connect Roy's Academy at 8910890311. Repeating the number again, 8910890311. Or another number, 8910600503. Repeating the number again, 8910600503.
All right, welcome everyone. Today we're diving into something that is, no joke, a kind of cosmic yardstick. It's a fundamental idea in geometry that lets us measure, well, pretty much anything, even stuff that's impossibly far away.
So to really wrap our heads around how powerful this is, let's kick things off with a question. A puzzle that, at first glance, seems absolutely impossible to solve.
I mean, seriously, how do you measure something you can't even touch? Like the height of Mount Everest, or the distance to the moon. You can't just take a measuring tape up there, right? So how in the world do we get those numbers?
Well, the answer, the big secret, isn't some crazy high-tech gadget. It's an idea, a really powerful mathematical principle called similarity. And it's what lets us measure these massive, immense things without ever leaving the ground.
Okay, so let's break this down. If we're going to use similarity to measure a mountain, we first have to know exactly what similar means in the world of geometry. It's a bit more specific than how we use it in everyday conversation.
You've probably run into congruent figures before, right? Think of them as identical twins. Same shape, same size, a perfect match. Well, similar figures are more like family. You can see the resemblance. They have the same shape, but they aren't necessarily the same size.
I mean, think about it. Any circle you can possibly draw is similar to any other circle. A tiny one, a giant one, they all have that perfect circle shape. The same goes for squares and all equilateral triangles. Their basic form is always the same.
And this leads to a super important point. It's a bit of a brain twister at first, but it makes perfect sense. All congruent figures are similar, right? I mean, if they're identical, they have to have the same shape. But, and this is the key, not all similar figures are congruent. The family resemblance doesn't make them identical twins.
All right, let's get down to the nitty-gritty. In math, we can't just eyeball it and say, yeah, those look similar. There are rules. 2 of them, in fact. For any 2 polygons to be officially, mathematically similar, they have to check 2 very specific boxes.
And here's a perfect real-world example. Think about a photograph. You can have a tiny wallet-sized print and a giant poster of the exact same picture. They are similar figures. Every single part of the photo has been scaled up or down by the same amount. But all the angles, the corner of a building, the angle of someone's arm, they stay exactly the same.
So that photograph example, it perfectly leads us into the formal definition. Okay, here they are, the 2 golden rules of similarity, and you need both of them. It's not a choice. Rule number 1, all their corresponding angles have to be equal. Rule number 2, all their corresponding sides have to be in the same ratio. They have to be proportional.
And that same ratio we just talked about, that consistent number you multiply by to get from one shape to the other, that's got a name. We call it the scale factor.
Okay, so what if you have a pair of shapes where only one of the rules works? Is that good enough? Are they kind of similar? Well, let's put it to the test.
Let's check out 2 test cases. First up, a square and a rectangle. Do they have equal corresponding angles? Yep, they're all 90 degrees, so rule 1 is a check. But are the sides proportional? No way. One is stretched out. Now look at the second case, a square and a rhombus. We can make all the sides the same length, so they're proportional. But look at the angles. They're totally different. Rule 2 works, but rule 1 fails.
So what's the verdict? I mean, just look at them. It's obvious, right? Neither pair is similar. They don't have the same shape. The rectangle is stretched, the rhombus is tilted. They failed the visual test because they failed the math test.
And this just proves our point perfectly. You can't pick and choose. Having one condition isn't enough. It's an all or nothing deal. For 2 polygons to be similar, both conditions have to be met. End of story.
Okay, so now that we are experts on the 2 rules of similarity, let's bring it all the way back to that impossible problem. How does this help us measure a mountain?
Well, think about shadows. If you have a light source, like the sun, and an object, the shadow it casts creates a triangle. Because the sun's rays are coming in at the same angle everywhere, the triangle made by the object and the ground is similar to the triangle made by its shadow and the ground. And that is the whole trick. You have the giant, unreachable triangle formed by Mount Everest, but then you can take something you can measure, like a simple pole, and stick it in the ground nearby. It also casts a shadow, forming a small, measurable triangle. Because the sun's angle is the same for both, those two triangles are similar. You can measure the pole and its shadow, figure out the ratio, and then use that exact same ratio, that scale factor, to calculate the height of the mountain. It's genius.
So it all comes down to the power of two, those two simple conditions, equal angles and proportional sides. They combine to give us this incredible tool, this cosmic yardstick that lets us measure things we could never, ever hope to reach.
Which really makes you think, doesn't it? Now that you understand the principle, what else could you measure? How could you use this power of similarity to solve other impossible problems?
This was an initiative from Roy's Academy faculty team, and today we've learned on course CBSE Class 10, Subject Mathematics, Chapter 6, Triangles, Topic, Geometric Similarity, and the Principle of Proportion. For obtaining similar video explainers, please connect Roy's Academy at 8910-890311. Repeating the number again, 8910-890311. Or another number, 8910-600-503. Repeating the number again, 8910-600-503.